So the recording has started. Thanks for coming. It has been a long time having so many students and guests in a lecture theater for me. That was okay. So this event is also part of the National Science Week. It will be live streamed for that event, and it's also a seminar for my colleagues. Okay, and an undergraduate lecture. So I put everything together because there's so much interest in this algae bloom. And I thought, I want to share what I learned in the last month. And what I want to do today is actually, it's a little bit like an investigation, a forensic investigation, if you like. And I invite you to go with me onto this journey and try to understand the science behind this algae bloom. And try to understand how I think, how I approach things. All right, at the end, I try to be as quick as I can, only focusing on the key points, to give you space for questions. If you have questions, we can have a question session at the end if you want. There's no introduction, so you can read up. I just keep myself as mysterious as I can. You can just look it up. Believe me, I know what I'm talking about, okay? Alrighty. So this session, also here is my email on this first slide. If you want to ask me questions afterwards, just feel free to drop an email. Alrighty. So this seminar has 3 lessons, 3 mini lessons that are all, should be part, come in, here, some free seats at the front, that are all part of the story. Okay? After an introduction, I will talk about the oceanography of South Australian Gulf so that you learn a little bit what are actually the key features of the circulation, for example, in this area, so that you understand the spreading of this toxic algae bloom. And then I will feature in the lesson 2, and it's all part of this one hour or half an hour, however it will take, okay? So don't freak out, don't think it will be an entire afternoon. I will talk all about the growth of this algae. And it's very, very important. That's a very important part to understand what's happening, okay? And then lesson 3 are the model forecasts, because it puts stuff together. So I actually use an existing model that I developed some 15 years ago or so and put in a forecast model for the algae. Okay? And then I also want to make one comment on the suitability of satellite images to trace the algae bloom at the very end. All right. So the first important point is tell you more about what species we're talking about and what the effects are. First thing I want to show you is actually the timeline. So I told you that it's an investigation, and the first thing you want to know, where did it start? Where did it go? Okay, so it started, and you can see number 1 there in this. So for those of you who are not familiar with the Gulfs, okay? So we have 2 large Gulfs here in South Australia. One is the Spencer Gulf, and the other one is Gulf St. Vincent, shown here on this map. And you can also see the island in the south. That's Kangaroo Island, one of the most, or the most beautiful islands on Earth, I would bet. Okay? And the Gulfs themselves, while they're relatively large, so if you want to drive from Adelaide, which is shown here on the right, you drive all around to Port Lincoln, takes about, with breaks, maybe 7, 8, 9 hours, doesn't it? So that you have the feeling of the size of the Gulfs. The algae bloom was first discovered outside the Gulfs. The Gulfs are relatively shallow. They're only 10 to 50 meters deep. So very, very shallow semi-enclosed systems. And that's where the number 1 is. That's where the algae bloom was first discovered by a surfer and noticing effects like some effects to it. And that's the original photo published in the ABC. Okay, but it didn't stop here. It actually was then discovered inside the Gulf. That's where the number 2 is, at Edithburgh, in this corner, in mid-April, 1 month later. And then another 2 months later, up in Ardrossan and in Adelaide coastal waters. So that's the timeline. So if you're investigating a murder, this is the important timeline that you have to imagine. Something happened initially outside the Gulfs and then spreading inside the Gulfs on a time scale of 2 to 3 months. No reports, no significant evidence in the Spencer Gulf, in the big one. Okay, so indeed some reporting, you know, that the first evidences of dead fish on the beaches, and okay, then came these satellite images. Scientists use satellite images. You know, we're talking more about satellite images a little bit later, but you can see some red areas claiming that this is the algae bloom spreading. And indeed then newspaper reports with the algae bloom similar to the size of Kangaroo Island. Massive size algae bloom. Okay? All right, so that's a little bit the background or the introduction. That's the timeline, very important. So now you learned a little bit, you know, about algae blooms you may or may not. And you can apply your common knowledge. And I've just listed some common knowledge. Well, the first thing is that not algae are bad. There are good and there are bad ones. You know, pretty much the reason why we have marine food webs in the ocean is because of algae. It's because of the plankton. It's the good algae, you know, diatoms and stuff like that. And I come back to upwelling will be mentioned several times in this presentation. Upwelling is a process that actually enhances nutrient levels in coastal ocean, causing plankton blooms. And we are here on the doorstep of a large seasonal upwelling system. Every year we get nutrients pumped into the surface layer and triggering massive algae blooms. And that's the reason why our marine environment is so beautiful. That's why we get whales, why we have tuna industries, dolphins, everything, sea lions, seals, and everything. It's because we have that process of upwelling. So many harmful algae blooms are triggered by an excess of nutrients. That's why we just had a chat with a student who said, well, that's too much nutrients, called eutrophication. You heard about that. Okay? And you probably know that we had a big algae bloom in the Murray River just recently. Big fish kills. Mm-hmm. So marine heat waves, you know, increasing in frequency and magnitude due to global warming increase the harmful algae blooms. We all heard that, and this is probably a summary that if you ask AI to write a little summary for you, this is what you get. Okay? And this is now you. Well, did we have any of these features in the region here in Adelaide, where the algae bloom started? Okay, so does this apply to all types of harmful algae blooms the same way? Can you always use these statements? Okay, algae bloom, okay, there must be a nutrient source. There must be a marine heat wave. There must be, oh, it's all global warming. It's easy. Okay? Or not. Come in, there's still some free seats here. That's very good. Okay? All right. This is so there are some speculated causes of the bloom. Okay, you find that on statements by the government. So, the River Murray flood in 2023, strong coastal upwelling in 2024, marine heat wave in 2025, eutrophication, global climate change, other, like diesel plant discharge. People say there was somebody, council member yesterday on the radio claiming it was the diesel plant, stuff like this. And at this stage, your investigation could be finished. That's all you need. You know, that's what you read in the newspaper. But is it finished? Is it just these things all together? Our prime minister will come for a visit next week, and he already made statements about global warming, and we have more algae blooms. But is this true? Okay. So these things here written down, not going too much into the details, are these stereotypes, coincidences, or true cause and effects? What you see here. So, and what I did is, I was not happy with this. First thing is, you want to learn about this particular algae. And what you do, you try to find a review paper, and if you're lucky, you get a very, very good one. And I got a very, very good review paper, and that's included most of what I use and what I'm talking about today. Just a little list. I try to make it quick, just featuring on the key points. You know, accumulation of its toxins harms shellfish. It's a type of it's a dinoflagellate. At high concentration, the algae clog fish gills, leading to suffocation and death. You know that. First described in 1935 by Japanese scientists. Fish gills and blooms reported worldwide for over 100 years. And this is the paper. It lists all the events. If you send me an email, can you send me a copy of this presentation? I do that. Okay, so you can take photos if you want. Reported worldwide, cost damage worth 2 billion yuan in Fujian province and China in 2012. It's $500 million Australian dollars, can cause massive damage. Spreading by currents and bioinvasion. And these two things you didn't see on the list that I showed you before. Currents comes from the evidence that it starts in one region, and then years later you can see it actually moved to a neighboring region, and there's a current actually in that direction. So this is the spreading by currents over time. You can trace the bloom movement. Bioinvasion is the conventional, unfortunate ballast water discharge. Ships getting rid of ballast water and discharging it. Okay, it's hard to prove. It's hard to prove, you know. But if you're interested in examples, have a look in this paper. They occur over a wide temperature and salinity range, and that's the key. And I focus on that in the future. So the first lecture, just the 2 slides or 3 on the oceanography. So what's important about the oceanography of the Gulfs? And just go to this map. On the left side, you just see the depth of the Gulfs. How deep is it? And in terms of colors, if you're hopefully not if you're colorblind, might be a little bit tricky. But you know, you can see it goes from up to 50 meters, and wide is something like 20 to 30 meters. So they were really shallow gulfs. And I also feature is number 3 is something we call Investigator Strait. It's actually a connection north of Kangaroo Island, number 3, that will be mentioned later. And number 4 in that, there is a very narrow passage which is called Backstairs Passage. And you can go and see Kangaroo Island. If you just drive to the south, go to Deep Creek Conservation Park, there's some beautiful lookouts, and you can see Kangaroo Island. It's a very, very narrow passage, but has very strong tidal flows. You know, maybe some of you have heard we have a feature here in South Australia which is called the Dodge tide. The tide almost disappears, yeah, on a fortnightly basis. But on the other hand, in this region, we have also on the other face of the tides can be 2 to 3 meters per second. So if you plan to go with a canoe, paddle over to Kangaroo Island, please check the tide forecast, because 2 to 3 meters per second from the side, it is very dangerous, okay? So what the feature, ecological significance, I have to cut it short. Most important features are actually located in the Spencer Gulf. We have a large sardine stock, and this is why the southern bluefin tuna come into the area to feed on the sardines in the lower Spencer Gulf, in that big area. This is why there's an extensive tuna industry in that area. In the very top, in the upper Spencer Gulf, we have the giant Australian cuttlefish at numbers exceeding 200,000 animals that come to lay their eggs in the very, very top regions. Okay? And as I said before, connected to the upwelling system, you know, which happens in the deeper regions on the continental shelf. And these systems are large inverse estuaries. We don't have much rainfall. We have excess of evaporation, and because of that, these systems are hypersaline. The salinity is higher than in the ambient ocean. And the way they operate, and this will play a role in understanding the spreading of the algae bloom, is that they produce an outflow of hypersaline water, and that sucks in ambient seawater into the Gulf. It's a little sketch here on the right, and this is we call flushing. So now you can imagine that if you have that outflow and you have something can get sucked into the Gulf and spread into the interior. So what I did some 15 years ago is I developed a model, a computer model, 3-dimensional model that can simulate, and here is just some snapshots of, on the left side is near surface temperature. And you can, if you look at, I run it again in a second, but you can see the month. It's 1 month later, now it's October, now November, December, now January. And so, and the colors is red is warm on the left side, blue is cold. And you can see how the temperature changes from 1 month to the next. It's the first. The second one shows you the salinity, but near the seafloor. Red areas are hypersaline, 40 grams per liter, as opposed to 36 in the ambient ocean. In these maps, you always have to try to find Kangaroo Island. It's that island, and then you can see both gulfs, and you get a little bit. Otherwise, you get lost a little bit. Okay, so there's this model. And what's also shown on the right-hand side is something we call the water age. And I just want that you get a feeling of what flushing means. On the right-hand side, it tells you how old, it's a theoretical method, how old the water is compared to water in the adjacent ocean. Okay, so the 0, you can see, is all that purple area is, you know, and then if you go into upper Spencer Gulf, the water age exceeds 1.5 to 2 years. What it means is it takes a very long time to flush this area with seawater, to bring seawater in there, and that's why this area is actually so special. Okay? That's why the giant Australian cuttlefish is actually in that area. It's more like a lake-type isolated environment because it has very, very slow flushing. And that's why it's also why it's hypersaline. You know, if you flush it immediately, it would have the same salinity as the ocean water. Okay, don't waste your time with that. We come back to that because that model I will use to predict the algae bloom development. Now all about the growth of the algae. So I was not happy with speculations or that common knowledge, or you just need nutrients, you need light, you need coastal pollution, and you get your algae bloom. I was not happy with that. I wanted to learn more. And I wanted to actually simulate it with a computer model. You can't just make speculations. I really want to have an equation. I'll show you equations. You will have nightmares and sleep bad because of this, but I don't care much, okay? So first of all, the key in all of that is indeed the algae growth. And algae growth is just a combination of cell division. Yeah, you start with 1, you make 2, but also a little bit growing each cell. You have 2, you have 4, growing again a little bit. And you can see that. So how many cells do you have after 20 divisions? What do you reckon? How many do you get if you do that? A million. Who said a million? That was perfect. You've seen it before. But it doesn't go on forever. But this only if all the ambient conditions are right. You know? So it depends on, light can't grow in the dark. All right. So, and you can describe this type of thing with an equation, and it's something like this. And I just want to show you what's done here. On the right-hand side, it shows you growth or sink terms. There's a growth term. P is just the algae concentration. There's a growth term, positive, and then you have motility, which is negative, and you have added a third term, zooplankton grazing, zooplankton that feeds on the algae. And if you know all these, there are parameters. There's the Greek letter mu there, which is the growth rate, mortality. If you know all of this, you can actually make a prediction into the future, which is on the left side, the rate of change of the concentration. So all you need to do is you need to know the terms on the right side, all these parameters, and you can plug it then into a loop. It goes and makes predictions and predictions and predictions. Okay? So now what makes it more complex is that the growth rate, this letter mu there, depends on light, nutrient levels, temperature, and salinity. So it's not a constant, it's just a change. It depends on where you are, it depends on the time of the day, whether it's nighttime or during the day. Before I show you actually the exact form of this growth rate, which is extremely important here, I just want to show you the solution. How does it look like? You can, if you have no zooplankton grazing, and with constant parameters, this mu and m constant, you actually find mathematical solutions. How does it look like? And this is shown now on the next slide. Okay? There are 3 curves. The dashed curve is the one if you don't have any mortality. If you just have exponential growth, what we started with is cell division. And the x-axis is in days. You can see 10 days, 20, 30, 40. And you can see it just explodes and goes to very large numbers within a short time. However, if you have a mortality in there, and this is the red curve, you start at very low levels, and then it increases initially at the same rate as this black dash curve, but you get an equilibrium. You can see here after 20, 30 days, you have an equilibrium. And that equilibrium is given by that ratio, the growth rate divided by that m parameter. And that's a very interesting thing, because there is an important conclusion that you can make already from this, is that this growth rate parameter determines the initial growth, how fast it initially grows, and it also determines the equilibrium level that you get at the end. So it all hangs, there is the mu is everywhere. The other message from this little curve, that's another curve, sorry, yeah. This is the blue one. It's also, if your initial concentration is too high, it will actually adjust and become lower and also approach that equilibrium. And you'll see that later on, if it gets colder, the growth rate becomes smaller, you get actually decrease in the equilibrium level. I know it's going to kill you, this one, but I don't let you go. There's one more message in this. How long does it take? Have a look at that graph. Tell me, how long does it take for an algae bloom to develop until you get an equilibrium? How long does it take? 25 days. Yeah. So not 2 years, not a year. So if you think about it, what do you think? There's a Murray River flood in 2023. You think it can cause an algae bloom 2 years later? You know, this is an important time scale. You are in a forensic investigation. It's all about time scale is very, very important. So if you have something initially, it takes 10, 20 days to develop. It's, you know, okay. All right. There's still. So now, and you might be surprised by at least one of these statements. Light and nutrient trigger values. You need light and you need nutrients in order to trigger the cell division. Light can, this K. mikimotoi algae can grow under very low light conditions. Sort of at 1 watts per square meter, which you still find during the day at 40, 50 meter depths in the oceans, still supports half the maximum growth rate, shows still significant growth. And there is no limitation. It grows during winter time, almost at the same rate as during the summertime here in the Gulfs, in the shallow water. And that's an important information, because you might say, oh, wintertime, light levels decrease, it will just disappear. Okay, light, no limitation. Now comes even the better one, nutrients. Nutrient limitation. What nutrients? Do you need nutrients? This particular algae has the ability, and here's the reference of where you find that, the links to other. It has the ability to grow at low mineral nitrogen concentration, mainly thriving on ammonia. Low ammonia levels of only this level here still support half the maximum growth rate. So the growth is not limited by light, it's not limited by nutrients. You don't need nutrients from a river. You don't need nutrients from upwelling. Nothing. All you need to do, put it there, and it will just kick off and grow. That is absolutely relevant. It's not to do with eutrophication in the ocean, not with pollution of the algae bloom has not started in the area where we have the most polluted waters along Adelaide metropolitan coastline, where large areas of seagrass were lost in the last 50 years. Okay? It started outside the Gulf in areas actually without much human pollution effects. Okay? And that's a big piece of information. And all because you found this one good review paper. It says everything. You need to just find it and read it. Okay, this is one. Now I want to show you curves. Let's check my timing. How's my timing going? My timing is good. Halfway. Halfway, and I was so nervous about this. It's already half gone. And then I regret what I did or said or something. I don't know. No, it's all solid. It's all solid science here. There's no speculation in it. It's all based on We know about this particular algae for more than 100 years. There's so much investigations about it, and we know the growth rate. Look at that red curve. I want to talk about that. This is the growth rate under optimum light and nutrient conditions. You just assume you're in a lab, essentially, you have enough ammonia in the water, you have enough light levels are good enough, and you do a test. You do test, how does the algae growth depend on the temperature? And you think, oh, bloody, I've seen so many curves in my life, but this one is an important one. You see, it cuts through the x-axis and it actually turns to 0. The red curve. You see that? This is what we call a trigger value. This algae cannot grow in water less than 12 degrees Celsius. Not an issue for us because, you know, the water gets pretty cold, but still, you know, I think it still doesn't get not 12 degrees. Okay? But more importantly, look at the red curve and look at the maximum. The maximum, where do you see the maximum? Between 20 and 25 degrees Celsius. So if you're, say, at 20 degrees and you change by 5 degrees, big warming. Whoa, what a marine heat wave. Growth rate is exactly the same. So a marine heat wave has no significant impact on the growth rate. You put it into water, which is 20 degrees, the growth rate is the same as if you have 25 degrees. There's a little bit of an effect if you compare 15 degrees and warmer water and 20 degrees, you can see where the slope is. But if you're in the warm region, it doesn't matter whether you have a marine heat wave or not. That is important information, isn't it? Your forensic investigation, you get somewhere. Because it's not the marine heat wave that caused the algae bloom. Because the growth rate is the same. Now on the right-hand side, and this is the very cool, and it is in this review paper, you know, and many, they done some computer simulations before, but in many studies, salinity is not included. But in this review paper, there is one reference there, Nielsen and Tonseth. It includes temperature and salinity. So on the left-hand side, I just show you this equation for a constant salinity of 35. And on the right-hand side, I just choose 20 degrees and show you the salinity effect. So look at that blue curve. Is salinity parts per thousand is the same as grams per liter. Okay, don't get confused with the units. Same units that we had before. And remember that the gulfs had salinities higher than 40 in the upper reaches. So you can see on the right-hand side, well, very hypersaline water reduces the growth rate. So there's actually hope that if the algae gets into the upper Spencer Gulf, that it will not grow significantly because of the salinity effect. It also does not grow below something like 13 grams per kilogram. So it's essentially in freshwater environment, it does not grow. Cannot grow because it needs seawater or something which brackish water, seawater, and has sort of optimum growth rate between 25 and 30. You know, 35 is the typical ocean salinity. It's pretty much there at the top. Very, just bloody curves there, red one and blue one. Very important information in that. That's the key. That's the key to understand this algae bloom. Okay? And all published, 91, that is something like 26 years ago. Okay? So growth rate vanishes to 0 as the water cools down to 12 degrees. But you can also play around with this because we have a seasonal cycle of temperature. I showed you that animation. The temperature changes. Warm during summer, cold during winter. There's a seasonal cycling of the growth rate. So you expect in warmer water, it will grow faster, and in cold water, it will become dormant or, you know, almost dormant. All right. Do you want to stretch a little bit? I'm rushing too much, hey? But it's not that much, not much more. If you study an algae bloom anywhere, you heard about algae blooms of California, find out which species it is and find out what's the growth rate. This is the key. Don't just come with speculations that it's like, you know, that's absolutely the key. Because I can now use this and can plug it into my computer model and I can do predictions. You know, because I know what the growth rate is. I can assume there's enough ammonia. You know, you can look up some levels of ammonia found in the Gulfs. Sufficient there, you don't need any limitation. And you can use a light effect because you don't want to have growth overnight, so that you can implement that. Okay, so the light effect, in a sense, you have maximum growth during the daytime and no growth overnight. So, and then you can do model forecasts of this bloom. And this was the initial aim. You know, I want to simulate it in a model. And by the way, I learned so much even before doing this simulation. Will it work? Not sure. Let's see. Let's see whether it works. So what I essentially do is I have the same model domain, both Gulfs, a three-dimensional model, not only two, 3 dimensions. And what the model actually includes is it includes tides. It simulates the tides, and it simulates the average currents and slow circulation that I showed you in the animations of the outflows and the inflows. And it doesn't include any heat wave or any other. It's based on average conditions, average winds, averaged over 10 years, something like that, okay? Coupled with a mikimotoi prediction model, including growth, mortality, zooplankton grazing. Is that little equation that I showed you? And it also includes now transport by currents and steering by turbulence. So you put a patch in there, into that model, and then it can disperse or it can be moved around over time. And wherever it goes and during which time of the year the growth rate changes. Because the growth rate depends on the temperature, on the salinity, and so it's mind-blowing, isn't it? So you put these things together, you don't know what happens, but you know initially, it's this a little bit bad, this color, the yellow little box there, the rectangle, this is where it's not particles, where the concentration patch is instantly released. 1,000 cells per milliliter, released on the 1st of March 2025. You know, just a once-off release, and then see what happens. What happens with that? Okay. There is one assumption, and the one assumption is, and nobody knows this, what it is a constant zooplankton grazing rate. It's something you assume that there's zooplankton there, and they always graze at a rate of something like 10% of the available algae biomass. You have to make assumptions because we don't know that. You know? So let's see what happens, what the simulation is. I show you animations, and they're only every month. I show you monthly average for March. It actually starts in January, but I show you several times. We have a little bit of time. This blue is nothing. And then you can see March, April, May, June, July, and we're here, August. And I will show you that several times. Blue is nothing. Red is the maximum. In this example, it's there, the red is 150 cells per milliliter, which means 150,000 cells per liter. So if you want to confused about the units. Okay. So that's what we get. And if you look closely, the first thing, and I show you that again, the first thing you see is the strong tidal steering across backstairs patch actually mixes it into the Gulf. And then it gets sucked in by this circulation. You have the outflow, but you get sucked into the interior of the Gulf and spreads across most of Gulf St. Vincent. And this reproduces the observed timing of the bloom that I showed you very, very early, with the 2 to 3 months. Okay? That's good. Okay. And that made me very optimistic. Not optimistic in the sense that the algae bloom will disappear, but optimistic in terms of that you can use the model to actually predict the algae bloom. Because one question that I had immediately is, why does it, I have it here as a little pop-up. Hang on a second, what makes the algae bloom weaker? Well, what makes it weaker in this model is there's a constant rate of zooplankton grazing, but the growth rate becomes smaller because as the water gets colder. The water gets colder, the growth rate decreases, you have more relative to that grazing, and the concentration drops. If you now hear today, they released statements that the algae concentration has actually increased along several jetties near Adelaide. That's not included in the model. The model assumes there's zooplankton everywhere. So if you think now that or if you assume that there is less zooplankton in certain areas or during certain times of the year, indeed you can have, even during wintertime, you can have a growth continuing. In this model with a constant sink of zooplankton grazing, it disappears. But it does not disappear. It just becomes weaker. Because I wanted to do the model and now do a forecast. Because this is a model that just simulates January conditions and goes on through the year, but then for the next year can do it too, and for the next year too. So what happens in the next summer? And that's a concerning part. So, that's a really concerning part. And this is the worst case scenario I show you in the model. If you have lots of zooplankton grazing, it will not happen. But I show you what happens. Now we are in August, we go into the future. September looks better. October, look at that. November, very high levels. Both Gulfs. Goes into February, goes March. Hey, this is massive, isn't it? Okay. It's scary, but how did it get into Spencer Gulf? How did it get into Spencer Gulf? And I go back to the initial one. You can see, just going back one, which goes to August, and you can see there's already a little bit in Spencer Gulf. You see that little patch? It even starts a little bit earlier. It's in May. There's already something in. There's some seeding of low concentrations of algae. And then with the next warming, it just kicks in with the cell division and the exponential growth, and and this indeed is very concerning. It can't disperse because we're all semi-enclosed. It can't go anywhere. Okay, I'll just show you the prediction, and that's indeed is very concerning. And I will give you a little bit of hope in a minute. Why did that door open? It's interesting. Oh, I said something wrong. There's a keyword and then the door opens. Hang on. There's even a little bit more concerning than this. Because if you know about the currents on the southern shelves of Australia, there's the possibility we have on wintertime, we have the Leuven current coming all around and going all along the coast, that this actually spreads to the east and potentially goes into a bass strait. You know, during summertime we have coastal currents that go the opposite way to the west, go all the way to the corner to the southwestern corner of Australia, influencing that area. This is very, very concerning, and we never had that before. And you can see that a little bit spreading out of Baxter's. That's the Baxter's passage. Okay. Did I forget anything? I'm talking so long on this aspect, maybe I forgot something. No, I think I made the key points. I want to talk about, just before I come to the end, satellite images. You know, some people use satellite images. You can determine the color of the water, something. I'm not going too much into the details in, you know, what this is, satellite chlorophyll A, the red patches, you know, but it's tricky. In very shallow water, you get first of all, you have other algae blooms, plus you can also have some sediment stirred up, and it looks like you have algae bloom, but there is nothing there. Anyway, this looks really good. This is tracking the algae bloom in terms of the red colors, and just starting in March again, top left, then April, top right, May, June, July. Tricky to get these images because satellite images are biased by clouds, and these are the only cloud-free days. Clouds is when you see white in these images. You know, that's cloud. These are the only days where you had truly almost no clouds. Okay, and you can see something. On the 14th of April, top right, you see this big red patch in Investigator Strait, you know, and that was basis of that assumption that you have the size of Kangaroo Island, the algae bloom. Okay, but you have to be very, very careful, because you can say, okay, we're not going out doing any measurements. We take satellite images. It's much cheaper, easy to do. And then in the next summer, you see images like this, and the public gets panic. Because, is this really the algae bloom? And I want to give you one example. I'll show you one example. What about this image? Have a look at this. I have one image of, it looks pretty much the same, doesn't it? Compared to 14th of April. But what time is it from, this image? What do you guess? This is the little bit the fun effect at the end of my lecture. Look at that, 2024. A year earlier, there was no algae bloom. And the only reason why I do this is I don't want satellite images to be used to make panic to people. We need boats out measuring algae cell concentrations, not these satellite images. Don't use satellite images. Because people freak out when they see red, you know, red traffic light, have to stay red. No, this is not the algae bloom. This is a year earlier on the right. No algae bloom. And that's an important, that's all you need to do to actually contradict. And I'm not saying that on the left it's not the algae bloom. But you need to have ground proofing to be sure that it is the algae bloom. On the right side, it's not the algae bloom. You're very sure of that because it wasn't there. I know it's over the top, but in a couple of weeks you will turn around and then you dream it. It repeats in a dream and then you... All right? So, summary and recommendation. The growth rate is the key in the understanding of this bloom. Growth rate is the most important thing. And I'm not repeating what I said before. There were very important points. It can be simulated with computer-based models. Ground truthing is desperately needed to monitor the spreading of the bloom across both gulfs. We need more than jetty-based measurements. We need people going out with boats and looking at the distributions, going to Lower Spencer Gulf and doing, you know, that's what's needed. Satellites cannot trace the algae bloom without ground truthing. It's an important message. Don't use satellite images. Future algae blooms in the Gulfs and the spreading along the coast possible. This is why you maybe need to also look at other regions to monitor the bloom. This is almost it. It's a bit of hope. And I'm not sure whether you get my bit of hope if you look at that. What's the bit of hope? Maybe you don't get it. I went with my family to the Onkaparinga river estuary. Lots of dead fish on the beach. Well, you don't know really how much was impacted. But you find dead fish on the... Look at that, there's these beautiful little birds. There is actually a natural response in the marine food web, because these algae, they're taken up by zooplankton. We don't know exactly how much or so. And the dead fish ending up on the beach, they're eaten by birds. So there's a food chain. First of all, it might actually control the algae in the future. We don't know how much. Don't think that my modeling is 100% right, because the big unknown is the zooplankton taking up the algae. Yeah, it might actually fully control it. And there's all these interactions. So it's not everything is dead and everything is dark, it's everything. There might be actually a boost in other parts of the marine food chain. It all depends on how bad will it be in the future. And I think my timing is almost perfect. I close this lecture. Thanks for coming. And maybe we can do a question if you want to. If you want to be recorded. If that works. Let's see. Thank you. Any question? Or you don't want to? You want to? You can. Because it's good for the recording.
Do you think it's this algae bloom is natural variation, or do you think it's produced by some industry or something like that?
This algae bloom was first named in 1935, and there's anecdotes that the similar blooms have been seen 30 years before that. So it's well at the beginning of the industrial revolution. It's not a man-made type of weird thing, and nobody knows how it started, but the idea is that it started somewhere, maybe where it was first discovered in Japanese waters, and then slowly spread by currents over the years. But here in South Australia, it's tricky because there is no, it was being reported in New Zealand, that's sort of the closest reports, but we are sort of the end of the world. This is the first time, and I would say this is the start of it. It's not coming from some mysterious currents from somewhere from Antarctica or from, because it was never found before. Okay? Does that answer your question? Maybe I answered another question too. Maybe it comes. Maybe it comes. The clue is around March, February, maybe late January. Have a look what happened during that time. Because it is, not the nutrients. It is you have to have some initiation of that event, and presumably something which already had a high algae concentration, localized.
Great talk.
Thank you.
I was just wondering what we know about how this species of algae has, how its populations have responded in other places where it's been introduced to. So you mentioned an algal bloom in Europe, I think. What's that population doing now compared to how it was in 2004 or whatever? You
really have to look up that paper because it varies. think the health minister said I heard that in the interview, there are cases where it actually was big and then went over a couple of years at low concentration, that came back. Other regions where it comes back on a regular level, some regions where it disappeared. It doesn't cause the same damage all the time, but never near something like what we have here, these inverse estuaries sucked into a system which is very, very sheltered and semi-enclosed. And that's, if it happens in the open ocean, like in the British English Channel, in that situation, it can disperse over time. Because it doesn't have that constraint. Yes, Bruce.
Jochen, predictably, I'm asking you about those rubbish satellite images. I suspect that you're using temperature from satellites. Is that true?
Temperature, no, this is chlorofillet.
But in your models?
In the models, there is absolutely nothing in there at all. The model itself only starts from some initial condition, and the only thing that forces us are winds, air-sea fluxes, precipitation, that type of thing. And then the model itself starts with an initial seed, no satellites, nothing in it, just standalone, runs on a little laptop computer, and you only look at the result, and that's what you then compare with the satellite images. No interaction whatsoever.
So obviously,
Thanks for coming.
It's a debate we can have where temperature is coming from spatially and temporally. But I'd like to talk about the more recent satellite images, which distinguish chlorophyll type. And I totally agree with you. We need ground truth to calibrate and validate all our observations, including satellite images. But I suspect that what a conclusion we should say is that we need better satellite images.
Okay, I take that as a comment. That's good.